Yo, welcome to Physics with Vinay. In the second lecture of kinematics, I'm going to start off with relative motion. So relative motion, if I have two particles, A and B, let's say, and velocity of A is VA vector and velocity of B is VB vector. Now these velocities are measured according to some observer. So usually in the questions, the velocities, if they just tell you velocity of a car is 50 meter per second, that velocity is usually given in the frame of an observer standing on the ground, or what we refer to as the ground frame. So if nothing has been said in the question, it's usually understood that those velocities are in the ground frame. So here, if I want to go into the frame of reference of A, if I want to see what A is observing for the motion of B, the velocity of B relative to A, so this is the notation that I'm using, this is velocity of B relative to A, or as measured by A, is equal to VB minus VA. So this is the relative velocity equation. Here VB and VA once again are measured in the same frame of reference. Usually it's a ground frame. Similarly, if I differentiate this once, I'll get my acceleration relation. So acceleration of B relative to A is acceleration of B minus acceleration of A. And if I integrate the velocity equation, then the integral of velocity is displacement. So I'll get displacement of B relative to A is equal to displacement of B minus displacement of A. Once again, these two quantities are in the same frame, usually the ground frame. So these are the equations that are going to be used in our relative motion topic. So let's look at a couple of questions based on these equations. So let's take a look at this question. This is one of the previous year's questions. So let's just read the question first. On a frictionless horizontal surface assumed to be the XY plane, a small trolley A is moving along a straight line parallel to the y-axis with a constant velocity of √3 - 1 meter per second. So this is my XY plane. I'm looking at the top view because this is the horizontal surface. So I'm looking at the top view and I have a trolley moving parallel to the y-axis. At a particular instant, when line OA makes an angle of 45 degrees with the x-axis, a ball is thrown along the surface from the origin. So ball is thrown along the surface. So here we're going to assume that the ball velocity is a constant along the surface. Its velocity makes an angle 60 degrees with the x-axis. So you should realize that the ball will be thrown at an angle of 60 degrees to the x-axis. Remember, it's all along the surface. Right, this is a horizontal plane, we are looking at the top view, and it hits the trolley. So find the speed of the ball with respect to the surface. So let's take a look at how we can solve this question. So I have my trolley A moving with some velocity, let's say VA, which is given to us as √3 - 1 meter per second. And at the instant OA makes an angle 45 degrees, a ball is thrown at 60 degrees to the x-axis. Alright, so this ball that is thrown at 60 degrees will eventually collide with the trolley. The trolley is also continuously moving. Now in order to solve this question, it will be best to go in the frame of A, because in the frame of A will become stationary, and therefore you will know exactly the angle that the ball makes with the x-axis. The ball will have to travel along this dotted line. In the frame of A, remember, A becomes stationary, and therefore the ball velocity of ball with respect to A has to be along the dotted line so that it goes on and hits the trolley A. So therefore, velocity of the ball with respect to A makes an angle of 45 degrees with the x-axis, therefore its components are equal. So now that makes the question very easy. So velocity of ball with respect to A, x component is equal to velocity of ball with respect to A, y component, because the angle of 45 degrees, the x and y components are going to be equal. So let's say velocity of ball is the speed of the ball rather is v, and it's making an angle of 60 degrees in the ground frame. So can I say that velocity of ball with respect to a would be velocity of ball x component, which will be v cos 60. And is there any x component for a? No, a is parallel to the y-axis. The velocity of a is parallel to the y-axis. There is no x component. And on the right hand side, I have velocity of ball. The y component of velocity of ball would be v sin 60 minus, what is the velocity of a along the y-axis? Root 3 minus 1. And that's it. All you need to do is solve for the speed v. So I'm going to have v sin 60, v root 3 by 2 minus v cos 60 should be equal to root 3 minus 1, and therefore you will get velocity as 2 meter per second. So this is the speed of the ball with respect to the ground frame. So it's a very straightforward question. Once you go in the frame of A, you can see the usefulness of the concept of relative motion. All such questions, see, any question that can be solved using relative motion can also be solved using just the ground frame. The frame of choice will not affect the physics. However, the choice of frame can definitely make a difference to the mathematical convenience of solving the question. For example, in this particular question, going in the frame of A is the quickest way to do it. It's a very straightforward, just one line equation. You just have to solve that algebraically. Alright, let's look at another question. So I have a shell is fired from a cannon on the ground with a speed 50 root 2 meter per second at an angle of 45 degrees to the horizontal. So this is a projectile motion. There is a bus moving away from the shell at a constant speed 20 meter per second. If the shell strikes the bus, find the distance of the bus from the cannon at the instant the shell was fired. So let me first draw the diagram. And actually, if you want, you can pause the video right now and try this question using the concept of relative motion, and then you can take a look at my solution. Alright, so first thing, I'm going to draw a diagram. So I have a bus, let's say B, and I have a shell that is being fired at 45 degrees with a speed of 50 root 2 meter per second. And we want to find this distance x. So x is the initial distance between the shell, let me call that A, the shell A, and the bus B at the instant the shell is fired. So what's going to happen in the ground frame is that the bus will travel a further distance and the shell is going to strike the bus. Alright, so you can definitely do this in the ground frame, but let me just show you how to do it using the concept of relative motion. So let's first go in the frame of the bus. So in the frame of the bus becomes stationary and the shell will perform projectile motion and hit the bus. So basically x becomes the range. What we are now left with is a projectile motion whose range is what we want to calculate. Alright, so can I write range as the x component of velocity into the time of flight? And can I write time of flight as, you know, we usually write it as 2u sin theta by g, but what is u sin theta? It is nothing but the y component of the initial velocity. So this is my range. Now all I need to do is figure out these components of velocity of the shell in the frame of the bus. That's it. Now this should be very simple. The bus is traveling with a speed of 20 meter per second. So initial velocity of the shell with respect to bus, the x component of that is going to be, what is the x component of the shell in the ground frame? 50 root 2 cos 45, so that is 50, minus the velocity of the bus is 20, this is 30 meter per second, so I have ux as 30. Similarly, what is the velocity of the shell with respect to bus, the y component of that? 50 root 2 sin 45, so that will be again 50, and there is no y component for the bus. So that's it, my range, and therefore my x value is going to be 2ux uy by g as we found out here, and ux uy everything is in the frame of the bus, so ux is 30, uy is 50, and we can take g as 10, so therefore I will have x as 300 meters. So that is the initial distance between the shell and the bus. You could have done it fairly easily in the ground frame as well, so pick whatever method you are comfortable with. but I personally would definitely prefer the relative motion method. Now let's look at two bodies in free fall. So by free fall I mean that the motion is only under gravity. There's no other force acting. So in this particular situation, relative motion becomes the best way to solve such questions, because see, if I have particle A and particle B, both their accelerations, irrespective of their velocities, will be g vector, g downwards, because it's under free fall. Velocity of A and B can be any direction, doesn't matter. And therefore, the relative acceleration, if I say acceleration of B relative to A, will become 0, and therefore velocity of B with respect to A will become constant because it has 0 acceleration. So this makes it very easy to solve such type of problems. We'll look at a couple of these kind of problems. Here an additional important point is the significance of this equation. Velocity of B with respect to A is a constant. That means not only is the speed of B relative to A constant, but also the direction. So direction of B relative to A is a constant, direction of motion of B. And that means in the frame of A, B just travels in a straight line. Now this makes calculations really easy. You can see that this also implies that the shape of the trajectory also depends on the frame of reference. In the ground frame, if I have velocity of A this way, velocity of B this way, they're going to perform projectile motion. But relative to one particle, the other particle is going to perform straight line motion. And therefore, you have to realize that the shape of the path taken by a particle can also change depending on the frame of reference. Alright, so let's look at a couple of questions based on this, and we'll see how this concept makes calculations really easy. So let's take a look at this question. Particle A is projected with speed 10 root 2 meter per second at an angle of 45 degrees with the horizontal from the top of tower of height 10 meters. So this is 10 meters. Simultaneously, particle B is projected horizontally with a speed 10 meter per second from the top of another tower of height 20 meters. So from here, and these two particles collide in mid-air. Find the horizontal distance between the towers. Alright, so I want to find this value of r, that is the horizontal distance between the towers. So relative motion will be the easiest way to do this. So let me just go in frame of one of the particles, choose any particle, doesn't matter, let me choose particle B. So in the frame of B, what is the initial velocity of A? So velocity of A with respect to B, the x component is going to be velocity of A x component minus the x component of velocity of B. So what is the velocity of x component of velocity of A? 10 root 2 cos 45. That will simply be 10 minus velocity of B x component would be minus 10. I have taken x axis this way and y axis in the upward direction. So I have taken x axis to the right hand side as positive. So velocity of B in the x axis x component would be minus 10. So this will be 20 meter per second. And velocity of A with respect to B, the y component, will simply be velocity of A y component, because velocity of B has 0 y component. And therefore this is going to be 10 root 2 sine 45. That will be 10. So if I were to just draw the diagram here, the question says that the particles collide mid-air. So we already saw that because these two are projectile motions, in the frame of B, particle A is going to perform straight line motion because their accelerations are g downward equal. We saw all that analysis on the previous page. So in the frame of B, if A has to collide with B, the path of A in the frame of B has to be straight towards B. And therefore, I can say that the velocity of A with respect to B, let's say its angle is theta with the horizontal. So can I say tan theta is the y component divided by the x component? And from geometry, I already know what is tan theta. What is tan theta here? See, this is 10 meters and this is r, which I want. So I can write 10 by r. And I know the y component and x component of the relative velocities. The y component is 10, the x component is 20. So I'll have 10 by 20, and therefore my value of r is 20 meters. So even though this motion is projectile for each particle, we've actually avoided any projectile equations or any analysis of projectile motion. We've just gone in the frame of one of the particles, we've gone in the frame of B, you can even go in the frame of A, doesn't matter. And then we deduce that the motion of A has to be a straight line in the frame of B. And therefore, the velocity of A should be directed towards B for the collision to occur, and it's then a very simple case of equating the angle that the velocity makes and using that the value of the angle from the geometry of the problem. Alright, now let's look at another question, this time where the collision is not occurring. Let's take a look. So let's say I have two particles A and B on the same horizontal level, and A is projected with a velocity of 10 root 2 meter per second at an angle of 45 degrees, and B is projected with a speed of 20 root 2 meter per second, let's say also at an angle of 45 degrees. And the distance between AB initially is 100 meters. Acceleration due to gravity is g. So the question is asking, find the minimum distance between the two particles during their motion. So there's no ground here. It's not as if A and B are launched from ground. A can go below the horizontal level, B can also go below the horizontal level. So the question is asking us find the minimum distance between them during their motion. So pause the video and try it out. Go in the frame of one of the particles. That's the best way to do this. And then you can take a look at my solution. Alright, so I'm going to go in the frame of B. Now I know once again that in the frame of B, since both of them are performing free fall on the ground frame, in the frame of B, A is going to perform straight line motion. So let's first figure out the initial velocity of A. So let me take right hand side as positive x-axis and upward as positive y-axis. So initial velocity of A with respect to B, the x component is going to be uax minus ubx. So what is the initial velocity of A, the x component? That's 10 root 2 cos 45. So that will be 10. And what's the x component of the initial velocity of B? That will be 20 root 2 cos 45, but in the negative x direction. So that will be minus 20. So this will be 30 meter per second. And similarly, velocity of A with respect to B, the y component would be. So what's the velocity of y component of A? That will be 10 root 2 sine 45 minus 20 root 2 sine 45. So that's 20. That will be minus 10. So if I were to just draw the initial velocity vector of A with respect to B, the x component is 30. The y component is a negative 10. So the resultant velocity is going to be somewhere this way. So this is the initial velocity of A with respect to B. So in the frame of B, A is going to perform straight line motion along this red path. Alright, and also remember that the speed is going to remain a constant for A in the frame of B, because acceleration of A with respect to B is 0. Alright, so if you just imagine the trajectory of A from the viewpoint of B, B is stationary here and B is watching A just travel in a straight line motion along this red path. So the minimum distance between A and B would be this perpendicular distance. So this length is what we want. So this length L is what we want. So now it's very straightforward. I know AB is 100 meters. And let's say this angle is theta. So can I just write L is equal to 100 sine theta. Now what is theta? Theta is nothing but the angle that the velocity of A with respect to B is making with the x-axis. So I have 30, I have 10. So tan theta is nothing but 1 by 3, and therefore sine theta would be 1 by root 10, and this will therefore be 10 root 10 meters. So this will be the minimum distance between A and B during their course of motion. So once again, we've avoided any concept of projectile motion here. and therefore by going in the frame of one of the particles, the other particle just performs straight line motion at a constant speed, and that makes our calculations very easy. Now let's take a look at a very similar question. So I would suggest that you try it out and then you can take a look at my solution. Alright, so I have two ships A and B are 10 kilometers apart on a line running south to north. Ship A further north is streaming west at 20 kph and ship B streaming north at 20 kph. What is the distance of the closest approach? So let me just first draw the diagram. So this is a top view of the water where the ships are traveling. Let's say this is north. So this is the entire horizontal plane. Alright, so let's say this is ship B. So A and B are both on the north-south line. The distance between them initially is 10 kilometers. Ship A is traveling west at 20 kph. So ship A is traveling to the left at 20 kph. And ship B is traveling at 20 kph in the northward direction. So I want to find the minimum distance between them. So this is the top view. If I just redraw the diagram, let me say this is x-axis and this is y-axis. So the northward direction is the y-axis and eastward direction is the x-axis. So can I write initial velocity vector of A is minus 20 I cap and the initial velocity of vector of B is 20 j cap. Now if I go in the frame of one of the particles, let me go in the frame of B. Velocity of A with respect to B will simply be minus 20 I cap minus 20 j cap. So in the frame of B, B is stationary and the velocity of A would be in this direction. This is the velocity of A with respect to B. So you can see from this that the x and y components are equal in magnitude, so this angle should be 45 degrees. And what's the initial distance between them? 10 kilometers. So once again the perpendicular distance from B to the straight line of A is going to be the minimum distance. So this is what I want. And you should be able to see this is nothing but from the triangle 10 sine 45. So just 10 by root 2 kilometers. So that's it. That's the distance of closest approach. That's the minimum distance between ship A and B. Here you can also use calculus. You can write down the distance traveled by B and A in time t and then get the distance between them as a function of time and then minimize it. That's another way, and choose whatever you are comfortable with, but definitely the quicker method is this relative method. Now let's look at Rain Man problems, or it could even be a woman. No offense to anybody. It's just traditionally it's written as Rain Man. Let me write it as Rain Person. Okay, so Rain Person problems. So I'm going to take an example and we'll see this concept through an example itself. So let's say I have a person that is walking at, let's say, 10 meters per second. Actually, person walking at 10 meters per second is not even possible because Usain Bolt ran 100 meters in 10 seconds. So his average speed was around 10 meters per second. So let's say this is Usain Bolt. Alright, so Usain Bolt is running at 10 meters per second along the x-axis, which is the horizontal. Let me take the x-axis this way. And let's say rain is falling at 5 meters per second. So rain is falling vertically at 5 meters per second. The question that can be asked is, I'm going to find the angle at which Usain Bolt should hold the umbrella. He has an umbrella to obviously prevent getting wet. So the concept is that Usain Bolt will look at in which direction the rain is falling on him, and along that direction he will hold the umbrella. So very straightforward. All we have to do is calculate the velocity of rain with respect to Usain Bolt. So I can simply write that the velocity of Usain Bolt is nothing but 10 I cap. And what's the velocity of rain? It's all in the ground frame. minus 5 j cap. It's falling down so along the negative y-axis, and therefore velocity of rain with respect to the Usain Bolt will be minus 10 I cap minus 5 j cap. Now just plot this vector. So the vector you can see is in the third quadrant, and the angle with the vertical, usually they ask you the angle with the vertical. You can see the y component of this velocity of rain vector with respect to the person is 5 and the x component is 10. So tan theta would be 2. So the angle with the vertical at which Usain Bolt should hold his umbrella at is tan inverse 2. This velocity vector that I have drawn is rain with respect to the person. So person Usain Bolt is going to have to hold the umbrella at an angle of tan inverse 2 with the vertical in order to prevent the rain falling on him. Now let's take a look at the effect of wind on these type of problems. So what usually happens is, if rain is falling vertically, suppose, and you have wind blowing, let's say, to the right, so let's say rain is falling vertically with speed VR in the absence of wind. So when there's no wind, rain is falling vertically, but now a wind starts to blow to the right with, let's say, speed VW, and therefore the resultant velocity of the rain will simply be VR in the downward direction and VW to the right. So the wind velocity just gets added to the rain velocity, and if I take this as my I cap and upward as j cap, so I can just write my rain velocity will be VR minus VR j cap plus VW I cap. So this will be my rain velocity, and then they can give you an observer running at some speed. They can ask you at what angle the umbrella should be held. So now this is exactly like the previous problem like we did. Here we've just gotten the rain velocity in the ground frame by adding the wind velocity. Now let's take a look at a couple of questions. So let's just first read this question. A man running on a horizontal road at 8 kph, for him rain appears to fall vertically. So he increases his speed to 12 kph. Now he finds rain hitting him at 30 degrees with the vertical. Find the speed of the rain drops with respect to the ground. So let's first just draw the diagram. I have a person running with speed 8 kph. So let's say velocity of the person Vp vector is 8 I cap. Let me take this as I cap, and j cap is vertically upwards. So rain appears to be falling vertically. So let me just say that the velocity of rain is some Vx I cap plus Vy j cap. So this is the general expression for the velocity of range, and I need to find Vx and Vy. So the first information given to us is velocity of the rain with respect to the person falls vertically when he is running at 8 kph. So that means there is no horizontal component of the rain with respect to person. So the x component would be 0. So the x component of rain is Vx minus x component of velocity of person is simply 8, should be 0, and therefore the velocity of the rain has a horizontal component of 8 meter per second. So this is how we get the horizontal component of the velocity of rain. Now the next information that is given to us is, when he increases his speed to 12 kph, he finds the rain hitting him at 30 degrees. Alright, so because I have gotten Vx is 8, can I write velocity of rain is simply 8 I cap plus Vy j cap. We are still to find Vy. So now the person is running at 12 kph. So I can write velocity of a person now is 12 I cap, and therefore velocity of rain with respect to person, I'll just subtract these two vectors. So I'll get minus 4 I cap plus Vy j cap. Now if I were to just draw this vector, it has an x component of minus 4, so 4 to the left, and See, I know this Vy will be negative because I know that the rain is falling downwards. I've taken upward as positive j cap. So let me just write the magnitude of the vector as mod Vy. I know it's going to be in the negative direction. And this resultant is making an angle of 30 degrees to the vertical. That is what the information is telling us. So now it's very straightforward. Just from this diagram, can I say tan 30 degree is equal to 4 divided by the magnitude of Vy, and therefore the magnitude of Vy would be equal to 4 root 3. And I know Vy is negative, so basically I get my entire rain vector in the ground frame is, I know the x component is 8, I know the y component is minus 4 root 3. So 8 I cap minus 4 root 3 j cap. Now what are they asking us? They are asking the speed of the rain with respect to the ground. So just the magnitude of this. So the speed of the rain is going to be 8 square plus 4 root 3 squared, 4 root 7 kph. So that's my speed of the rain. Oh, sorry, I made a mistake here. The units is, the velocity of person is 8 kph, not meter per second. So let me just erase that. That should be kph. Alright, so that's your answer, 4 root 7 kilometers per hour. Let's take a look at another question. A man is coming down an incline with an angle of 30 degrees. So when he walks with a speed 2 root 3 meter per second, he has to keep his umbrella vertical to protect himself from the rain. So that means with respect to the person, the rain is falling vertically downwards when he is walking at a speed of 2 root 3. The actual speed of the rain is 5 meter per second. And what angle with the vertical should he keep the umbrella when he is at rest so he does not get drenched? So basically the question is asking us to find the angle that the rain is making with the vertical when the person is at rest. That means they're asking us in the ground frame. So if you want, you can pause the video and try it out. It's very similar to the previous question, and then you can take a look at my solution. Alright, so what I'm going to do is, let's say this is my x-axis, this is my y-axis. So the person's velocity is in this direction, Vp vector. It's 30 degrees to the x-axis, and the speed is 2 root 3 meter per second. So can I say Vp vector would be 2 root 3 cos 30 I cap, just resolving it in x and y components, minus 2 root 3 sin 30 j cap. So that will be equal to 3 I cap minus root 3 j cap. Alright, so this is the velocity of person in I cap j cap components. Now let's say that the rain velocity is some Vx I cap plus Vy j cap. So with respect to the person, this will be Vx minus 3 I cap plus Vy plus root 3 j cap. Once again, here Vy will be negative. Alright, so this is the velocity of rain with respect to person, and we know that the person has to keep his umbrella vertical in order to protect himself. So that means the velocity of rain with respect to person is vertical. Therefore, its x component is 0. Horizontal component is 0. Therefore, I can write Vx minus 3 is 0. So that way I get velocity x component of the rain. And because the speed of the rain is given to us as 5, can you simply see that Vy would be 4 with a negative sign. So if I just plot, I'll have rain with a horizontal component of 3 and a downward vertical component of 4, and that's it. The angle at which the rain will be falling with the vertical, so tan theta would simply be 3 by 4, which is approximately 37 degrees to the vertical. So this is the angle at which the person should hold the umbrella when he or she is at rest. Now let's look at riverboat problems. So suppose I have river flowing, let's say this is the x-axis, the y-axis across the river. So river is flowing along the x-axis, and we are looking at the top view. This is the top view of the river, and these are the two banks. And let's say there is a boat that starts out from one bank and wants to cross the river and reach the other bank. So in such questions, you will be given a phrase like this. You will be given speed of the boat, or it could even be a swimmer, a person swimming in still water. It's VBR. So what does this mean is that still water, the word still means stationary. If water is stationary, that means it's in the frame of the river. So when the speed of a boat or a person is given in still water, that means this phrase is giving us the speed with respect to the river. Alright, and let's say the river has a velocity of VR. And let's say the velocity of boat relative to the river is at an angle theta to the river flow. So in questions, they may phrase it like the person is trying to row the boat at an angle theta. So trying to row the boat means it's if the river had been stationary, the person would have gone along the direction which is making an angle theta with the river flow. Alright, so velocity of boat, I can just use my relative equation to write velocity of boat in the ground frame. So this is in the ground frame or the bank frame. It's nothing but the relative velocity plus the velocity of river. So this is just basically a relative velocity equation. So even though the boat is trying to be rowed in this direction, or the swimmer is trying to swim in this direction, in the ground frame, the boat will acquire a velocity of the river as well, and the resultant velocity will be in some other direction. The boat was trying to go along the blue path, but it will end up traveling along the red path. Alright, so let's say that the distance between the two banks is capital D. So first thing that I want to find out is how much time is the boat going to take to cross from one bank to the other. So basically I know that in crossing from one bank to the other, this displacement has a y component of D. This red path is my displacement and it has a y component of D. So I can write it as velocity of boat y component in the ground frame times the time taken to cross. Capital T is the time taken to cross. Now what is the y component of velocity of boat? That will simply be the relative velocity y component plus the river y component, but river has no y component. River is flowing along the x-axis. That will simply be VBR sine theta. The relative velocity is making an angle theta with the x-axis. And therefore, my time to cross would be D divided by VBR sine theta. So you should be able to see that this time will be minimum, keeping the speed constant. This time will be minimum when theta is of course 90 degrees. So when the boat tries to row perpendicular to the river flow, it will take the minimum possible time in order to cross the bank. Now let's calculate its displacement along the x-axis. So that is also known as the drift. So this is known as the drift, basically displacement, x component of the displacement. So I can simply write that as the velocity of boat, the x component multiplied by the time. So the x component of the boat will simply be VBR cos theta plus river speed is entirely along the river velocity is entirely along the x-axis multiplied by the time, and time was D divided by VBR sine theta. This is what we found on the previous page. Alright, so this is basically the expression for drift. For zero drift, you can see we just have to equate this expression to 0. That means the boat will have 0x component in the ground frame, and you can see cos theta would be equal to minus VR divided by VBR. So the negative sign denotes that the boat will try to swim upstream. Upstream means against the river flow. And the resultant will be perpendicular to the river flow. So this will be my VB vector. Now you should be able to realize that such a theta will exist only if VR is less than VBR, otherwise we will have no solution for cos theta. So if the river velocity is greater than the velocity of the boat in still water, then zero drift is not possible. However, we can still minimize the drift as the boat is rowed from one bank to the other. Let's do that on the next page. So we found out that the drift was VBR cos theta plus VR times d divided by VBR sin theta. So in order to minimize this drift, just use a bit of calculus, set it to 0, and you will get cos theta as minus VBR divided by VR. So this is a situation when drift is minimized. So we are talking about the case where VR is greater than VBR. So we will like to remember these two expressions for the zero drift and the minimum drift. Now let's take a look at a question. So let me just first read the question. A swimmer starts from point A on the bank of a 200-meter wide river, crosses the river in 5 minutes to reach the opposite bank. He returns to the point B on the original bank such that AB is 300 meters in the downstream direction. So find the magnitude and the direction of the velocity of the swimmer relative to the bank if his velocity with respect to river is always perpendicular to the bank. Alright, so lots of information in this question. Let's first draw the diagram. So the swimmer starts from point A. So I have my river velocity and let's say that is VR. And the question says that this velocity with respect to river is always perpendicular to the bank. So let me just write that as V relative. So V relative here, this labeling is for the velocity of the swimmer with respect to the river. It's always perpendicular to the river. So the resultant will be somewhere this way. Alright, so he is able to cross this 200-meter wide river in 5 minutes. So you should be able to see that the velocity of the swimmer, let me label that as V vector, in the ground frame, that is in the bank frame, will be equal to VRI cap plus V relative J cap. I'm taking I cap and J cap in this manner. And therefore, I also know the displacement, the Y component of the displacement, which is 200 meters. So can I just say 200 should be equal to V relative is the Y component in the ground frame multiplied by the time, which is 5 minutes. So that will be 300 seconds. So V relative will simply be 2 by 3 meter per second. So the relative velocity has a magnitude of 2 by 3 meter per second. Alright, the next information is he returns to a point B on the original bank. So first he travelled from A to some point, let's say C, and then he returns to point B, and this is 300 meters. So once again, the velocity of the swimmer with respect to the river is perpendicular to the bank. So that means this will be the velocity components from C to B, and therefore once again the time taken from C to B will be the same 5 minutes, because the Y component of velocity is once again has a magnitude of V relative. So from C to B the time taken would be once again 5 minutes. So therefore A to B the time taken would be 10 minutes. So what is the X component of the swimmer's velocity in the ground frame? That is nothing but the velocity of the river. So can I say V river times 10 minutes, which is 600 seconds, should be equal to the distance travelled, 300 meters. And therefore V river simply becomes half meter per second. And therefore my entire velocity from A to B at least is half I cap plus 2 by 3 J cap. So this is my velocity vector, and therefore its magnitude, it's all in the frame of the bank, would be, magnitude would be 5 by 6 meter per second, and the angle theta here, tan theta would simply be the Y component 2 by 3 divided by the X component, so that will be 4 by 3. So which is approximately 53 degrees. That's the way that the swimmer will travel. Now let's look at some calculus based kinematics. So in general, I can write that velocity vector, instantaneous velocity vector, is the rate of change of displacement, or I can also write it as the rate of change of position vector. So R here is a position vector, and S vector is the displacement vector. And instantaneous acceleration would be dv by dt, the rate of change of velocity vector. In one dimension, I can just write v is ds by dt. If it's along the x-axis, then I can just write it as dx by dt, and I can write my acceleration as dv by dt. So all of this is along the I cap direction here in this particular example of motion being along the x-axis. And another useful expression for the acceleration is I can just divide and multiply by dx, and dx by dt is nothing but velocity. I can just write it as v dv by dx. So these are the usual expressions we use for questions in which calculus is involved, where you have variable velocity varying with time or acceleration varying with time. So let's just look at a couple of questions based on these equations. So here I have a particle moves in the xy plane with velocity given as a I cap plus bx j cap, where a and b are some constants, and initially consider the particle to be situated at the origin. So it's at x0 and y0 at t equals 0, and find out the equation of the trajectory of the it says projectile, but there's a small typing error there. Let me just replace that by particle. Okay, so let's see how we can solve this kind of a question where you want to find the equation of the trajectories. So basically there's no need to involve time here, because we want the equation of trajectory. That means we need a relation between the y coordinate and the x coordinate. So I have v vector is a I cap plus bx j cap. So the x component of velocity is a, so can I write a as dx by dt, and can I write the y component of velocity bx would be equal to the rate of change of the y coordinate. Now I can just eliminate time right away by just dividing these two equations. So if I just divide these two equations, so let's say this is equation 1 and this is equation 2. So let me just do 2 by 1. So can you see on the right hand side I will get dy by dx, and on the left hand side I'll get bx by a. So I've eliminated time right away. Now it's very straightforward. I can just write dy is bx dx divided by a, and then you just integrate it, and we know that x is equal to 0 and y equal to 0 is the initial position, so the lower limits will be 0 0, and for some general x I'll have some unknown y, and this is a simple integration. So this will be the equation of the trajectory of the particle. So you can see that when we want the equation of trajectory, you can just eliminate time right at the beginning in this sort of an example. Let's look at another type of question. So I have a particle that is traveling along a straight line, so let's say along the x-axis, and the particle's velocity is given to be t squared, let's say minus 7t plus 12. So this is the particle's velocity given to us, and the question is asking find the time interval in which the particle is retarding. Alright, so the question is asking us to find those particular time intervals in which the particle is retarding. So here one common type of mistake that students tend to make is they think that retardation means acceleration is negative. That is not correct. Retardation implies that speed is decreasing, and speed is decreasing, that means that the acceleration and velocity should have an obtuse angle between them. So if I have a velocity vector, I'm just talking in general in 2D, 3D, and the acceleration vector of the particle is this way, so this angle is obtuse. So that this situation will imply that the particle is retarding. Why is that? So why is this implying that the particle is retarding? Is because the rate of change of speed is given by the component of the acceleration along the velocity vector. The speed is the magnitude of the velocity vector, so an acceleration is the rate of change of velocity vector. So the component of acceleration along velocity, if that is parallel to velocity, then the velocity magnitude will increase. If it is anti-parallel to velocity, then the velocity magnitude will decrease. Basically, particle is retarding if v dot a is negative. Basically, the dot product is negative, means that the angle between the two vectors is obtuse. And just for completeness sake, let me just write down that if v dot a is positive, that means velocity and acceleration have an acute angle between them, then the particle is speeding up. So speed is increasing. Alright, so now that you know this concept, if you want, you can just pause the video right now and try this question that I have given, and I'll solve it on the next page and you can have a look at my solution. Alright, so in one dimension, the particle will be retarding if acceleration is opposite to velocity vector. So if acceleration is anti-parallel to velocity vector. So velocity vector is in the right direction, acceleration is in the left direction, or if the velocity is in the left direction and acceleration is in the right direction. So in both these cases, the particle will be retarding. Alright, so for us, basically that will mean that a times v is negative. Now I had my velocity as t squared minus 7t plus 12, and therefore acceleration would be dv by dt. That would be 2t minus 7. So a times v should be negative. So a, I can just write it as twice of t minus 3.5, and velocity I can just split it into t minus 3 times t minus 4. This entire expression should be negative. Now this is very straightforward to see that the time intervals would be less than 3 seconds and the time interval between 3.5 and 4 seconds. So less than 3 seconds and then 3.5 to 4 seconds, these are the two time intervals in which the particle will be retarding. Let's look at another question. Suppose I have velocity as t squared minus 3t plus 2. So the particle is once again moving along the x-axis, and I want to find the distance traveled by the particle in, let's say, 4 seconds. Alright, so here the question is not asking displacement, the question is asking distance. What that would mean is we will need to figure out at which point the particle changes its direction, reverses its direction, and then we'll have to add up the individual segments traveled by the particle. So let me just first write down the velocity as t minus 2 times t minus 1. Alright, so if I just look at the intervals, so from t equal to 0 to t equal to 1, the particle is traveling in the positive direction. Then at t equal to 1, its velocity becomes 0. After that it becomes negative. Then further at t equal to 2, velocity again becomes positive. So we don't know exactly where it will be at t equal to 2, we'll have to figure that out. But t equal to 0 to 1, the velocity is positive. T equal to 1 to 2, velocity is negative. And t equal to 2 to 4, again velocity will be positive. So we have these 3 time intervals. So what I have to do is I'll have to integrate from 0 to 1, 1 to 2 and 2 to 4, and in 1 to 2 Since the velocity is negative, the displacement from 1 to 2 will come out to be negative, but I'll have to take the magnitude of that displacement and add it to the other two segments. So I hope that is clear to you. If you want, you can pause the video and give it a try, and then you can have a look at my solution. Alright, so the distance traveled would be, I will write integral v dt from 0 to 1 plus, when I write integral v dt from 1 to 2, like I said, the displacement, this is the displacement from 1 to 2, that will be negative. So I'll have to, because I want to find the total distance, I'll have to take the magnitude of this. Plus 2 to 4 v dt. Now it's just a basic case of integration, so let's just quickly do that. T square minus 3t plus 2 dt from 0 to 1 plus the modulus of integral from 1 to 2, t square minus 3t plus 2 plus the integral from 2 to 4, t square minus 3t plus 2 times dt. So I've just replaced the velocity by the expression given to us, and then it's a very simple case of integration, so you can do the calculation on your own, and the answer comes out to be 17 by 3. So this will be your final answer, the total distance travelled in 4 seconds. So be very careful in the question whether they are asking displacement or distance. Make sure you figure out where the velocity becomes 0, that will be the turning point of the particle in one-dimensional motion when you need to calculate the distance. Now let's look at sort of a different type of problem. So let's say I have a fixed point O, and let's say this is in 2 dimensions. So let's say the particle is initially at a distance of 10 meters and its velocity is always making this angle of 60 degrees with the line joining the particle to the fixed point O. So if I just label this as the position vector, what will be the angle between the position vector and the velocity vector? Remember, we have to join the tails in order to measure the angle between two vectors, so that will be 120 degrees. So let me phrase the question as, and this is the way it will come in the exam, the velocity vector always makes an angle of 120 degrees with the position vector. And let's say the magnitude of the velocity, the speed rather, is always a constant, and it's equal to 2 meters per second. Alright, so they can ask you find the distance travelled by the particle till it reaches point O. Alright, so if I want to calculate the distance, then because I know the speed, which is a constant, all I need is the time taken for the particle to go to point O. Then I can just multiply the speed and the time to get the distance. So in order to get the time to reach O, let us just first visualize what kind of a motion this is going to be. The particle here, let's say, is making an angle of, in general, let me take an angle of theta here. Now in dt time, suppose it travels a distance v dt, so it will travel a distance or displacement v dt. Now the position vector will change. The position vector, which was initially in this manner, now it will be in this manner. So once again, the particle's velocity, since it's always making an angle of 120 with the position vector, the particle's velocity will again make this angle theta. In another dt time, it will again travel v dt. The position vector will again shift this way, and therefore the velocity vector will also rotate. And you should be able to see that the trajectory of the particle will be something of a spiral. So this is just a diagrammatic representation of what is going to happen. I have obviously magnified the v dt displacements. In reality, they will be infinitesimal. So it will be a smooth spiral. Okay, so how do we go about solving this question? We have to realize that in general, if I have a particle, and this is my position vector, or let's say this is length is L from the fixed point O, and the velocity is making an angle theta at some instant. dl by dt, the rate of change of the length, is going to be the component of velocity along the length. So it's going to be equal to v cos theta. So when I break down this velocity into two components, it will be v cos theta and v sin theta. So these two components are going to play two different roles as far as L is concerned. V cos theta, the component along the length, is going to change the magnitude of the length. And the component of velocity perpendicular to the length, that is v sin theta, is going to rotate the length. V sin theta rotates the length or rotates the position vector, and v cos theta changes the magnitude of the length. So here we are only concerned with v cos theta. We'll discuss more about the component of velocity perpendicular to the length and how it rotates and what is the equation for the rotation when we study circular motion. So in this chapter we are only restricting ourselves to the study of the component of velocity along the length. Alright, now that I've taught you this concept on how to write down the rate of change of length in terms of the component of velocity, if you want you can pause the video and give this question a try and then you can have a look at my solution. Alright, so let me solve this particular question. Let me just do that on the next page. Like I said, if this O is fixed and this length is L and I have a particle which is making an angle theta, I can write dl by dt as v cos theta. So in our particular question, the angle is 120 degrees. This angle is 120 degrees. Let's say, let me call this position vector magnitude as r. So can I write dr by dt would be v cos 120. So dr by dt would be, the speed was given as 2. So 2 cos 120 would be minus 1. So the minus sign just denotes that the position vector magnitude is decreasing. As expected, it's going to spiral down to O. Ultimately, the position vector magnitude is going to go to 0. Alright, so that the minus sign just confirms what we already know. Okay, so you can see that dr by dt is a constant value. So basically this length is decreasing at a rate of 1 meter per second. Initially, the question gave us the length as 10 meters. So if it's decreasing at the rate of 1 meter per second, how much time will the length take to go from 10 to 0? That will be 10 seconds. So the time taken would be 10 seconds. And therefore the distance traveled would be speed into time. So 2 into 10, which would be 20 meters. So the particle is going to travel 20 meters along that spiral path until it reaches the point O. So in the previous example, we saw that this point O was fixed. Now let's say this point O also starts moving. So suppose I have point O moving with velocity v1 at an angle theta 1. Point P, velocity of point P is let's say v2, an angle theta 2. And let's say I want to write down the rate of change of this length. So it's very straightforward to see. You should be able to realize that point P velocity, the component of velocity v2 along the length is away from the length. So v2 is trying to increase the length. So that will be v2 cos theta 2, the component of v2 along the length. And component of v1 cos theta 1 is towards point P. So therefore v1 cos theta 1 is trying to decrease the length. So we will have a negative v1 cos theta 1. So I hope you understood how I wrote this expression. Once again, let me just quickly repeat it. Point P is trying to move away from point O. So the velocity component of point P along the length will increase the length. So we'll have a positive v2 cos theta 2. And point O is trying to move towards point P, trying to decrease the length L. So velocity component of O along the length, we will have a negative sign here. So this is dl by dt. And we'll use this concept more in laws of motion when we study string constraints, where we'll have to set the rate of change of length of a taut string to be 0. So we'll get a relation between the velocity components. So we'll look at that in the next chapter in laws of motion. Let's just do a kinematics question right now. So we're going to combine the concept that we just learned right now with river boat problems. So let's take a look. To cross a river of width B is 320 meters, a boatman steers his boat always aiming towards a point that is directly opposite to the starting point. So let me just draw the diagram for this. So I have the river, and let's say the boat is starting from point A. Point B is the point which is directly opposite to point A. So the boat is starting from point A, and as the boat travels, at any instant, the boatman steers his boat always aiming towards a point that is directly opposite to the starting point. So when I say that the boat is aimed at that means it is the velocity of the boat with respect to the water. So velocity of boat with respect to water is always towards point B. So velocity of the boat relative to the river current VBW is given to us as 2.5 meter per second, and the river current velocity is VW is 1.5 meter per second everywhere. So we've been given the relative velocity and the river velocity. Determine the time which the boat will take to cross the river. Okay, so the width of the river is given to us as B. So the velocity of the boat in the ground frame would be a resultant of the relative velocity and the river velocity. So that is given to us as VW, velocity of the water. So let's say at some instant the angle that this relative velocity makes is theta with the line along the river flow, and let me label the boat as C. So C is my boat. Okay, so there are two ways to do this question. One will be going in the ground frame, writing down the equations of the ground frame. The other method would be to go in the river frame. So you can get the answer using both methods, but let me just do it using the river frame. So in the river frame, the water is stationary, and therefore the velocity of the boat is simply its relative velocity to the water. So velocity of the boat, the speed of the boat will only be 2.5 meter per second. But here we have to realize that point B, which was stationary in the ground frame, will now itself be moving in the opposite direction to the river velocity. So it will be moving with the speed of VW to the left, and therefore the boat which starts from point A, its velocity is always directed towards B, and now that's velocity is just the relative velocity of the boat with respect to the river. So as the point B travels to the left, the boat will keep on following it such that its velocity is always directed towards the point B, and eventually it will meet. The reason it will catch up is because the speed of the boat relative to the water is greater than the velocity of point B. The speed of point B rather is simply the speed of the river. You can see the question says that the relative speed is greater than the water speed. So eventually the boat will catch up with the point B. Alright, so we need to figure out the time taken. So I'm going to do this in the river frame. Let me do the calculations on the next page. So let's say this is a trajectory of the boat eventually catching up with the point B. So everything is in the river frame that I'm going to write down. So this is the trajectory of the boat, but let's say at some instant the boat is here. So its velocity, let's say this boat is marked by point C. So the velocity of the boat is directed towards point B, and that velocity would be 2.5 meter per second, the velocity of the boat relative to the river. And velocity of point B is to the left, 1.5 meter per second. So let's say at some instant this angle is theta here. At some instant what I'm going to do is I'm going to write down the rate of change of some quantities. So let's say this length is x. Basically the displacement of the boat parallel to the banks. That component of displacement is x. And let's say CB is L. Okay, so I'm going to write the rate of change of these two quantities. There's another quantity whose rate of change we can write, but it won't be useful, which is this, let's say the y coordinate of the boat. You can write the rate of change for that, but I'll explain to you. You'll see why that is not useful. Instead, the rate of change of x and L will be the most used in this question. Alright, so can I say dx by dt is nothing but the component of velocity parallel to the bank? So let me just take the x-axis to the left and y-axis this way. So what I'm basically writing is the x component of the velocity of the boat. That will simply be 2.5 cos theta. We've assumed that the velocity of the boat relative to the river makes an angle theta with the bank or with the x-axis. And if I write dl by dt, see, I have my boat here and this point B. So this length is L and I want to write the rate of change of that, and we already saw how we can do that. So this velocity is 1.5, this angle is theta, and the velocity of the boat is 2.5. So can I write dl by dt? So we already saw this concept here. When you have like 2 points, point O and point P, which are both moving, and you want to write down the rate of change of length L, we were able to do that by writing the component of velocities of point P and O along the length. So that is what we are going to do in our situation as well. So velocity of B, what is the component of velocity of B along the line joining the boat and point B? That will simply be 1.5 cos theta, which is trying to increase the length L, and the component of velocity of boat along the line joining the boat and point B is simply the entire 2.5, but that 2.5 is towards B, so that is trying to decrease the length, so that will be minus 2.5. Alright, so I have two equations, and like I said, I could have written dy by dt also, but you should be able to see that dy by dt will have a sine theta term. It will be the y component of the velocity of the boat. And that will not be very useful to us because cos theta is appearing in both the equations that we've written down here. And what we are basically going to do is we are going to try and eliminate cos theta in order to calculate the time. So a sine theta term in the y coordinate will not be useful for us. Okay, so I'm going to integrate the first equation. So can I write dx is equal to 2.5 cos theta dt. Now in order to write down the limits, see, you have to understand we are working in the river frame, so the boat is going to travel something of this sort and eventually reach the point, catch up with the point B. So this will be x. So let's say that is x naught, the final x coordinate of the boat when it catches with point B. So can I write x coordinate initially was 0, finally it's x naught. Let's say 0 say t, and so I'll have x naught is equal to 2.5 times the integral of this cos theta dt. So I'm going to eliminate this integral by integrating the second equation as well. So my second equation, see, can I write dl is 1.5 cos theta dt minus 2.5 dt. Let's integrate this. Now L is the distance between the boat and point B. Initially what was the distance? Initially the distance was B. And finally what is the distance between the boat and point B? 0. Because the boat has caught up with point B. 0 to t, and this also 0 to t. So I'll have minus b is 1.5. Now what is the integral of cos theta dt? What is this value? Can I write it from the integration of the first equation? This value is nothing but x naught by 2.5. So that is what I'm going to substitute here. So I'll have x naught by 2.5 minus the integral from 0 to t will simply be 2.5 times t. Now it seems that we have two unknowns here, the time as well as x naught. Is there a way that we can relate x naught and t? If you want, just pause the video for a minute and try and think of how we can write x naught directly in terms of t. If x naught is the x component of the displacement of the boat, it is also the displacement of some other point that we know in the diagram. Just think for a minute and then you can continue the video. So x naught is not only the displacement x component of the boat, but is also the displacement of point B in time t. And point B is moving with a constant velocity of 1.5. So can I simply write x naught as 1.5 times t? All we have to do is substitute x naught here and then solve for the time t. So let me just do that on the next page. So my equation was minus b is 1.5 times x naught divided by 2.5 minus 2.5 times t. And I wrote x naught as simply 1.5 times t, which is the displacement of point B. All we have to do is just substitute the value of x naught. That will be 1.5 squared divided by 2.5 minus 2.5 times t. I have just substituted x naught here. And that's it. We were given b as 320 meters. So just solve for the time taken and you should get your answer as 200 seconds. So I hope you were able to understand how we were able to go in the river frame and solve this using the concept of rate of change of length, the concept that we learned and applied here. Now I'm going to just slightly change the question and give it to you guys to solve. Okay, so in the question that we just solved, I'm just going to change a couple of things. That river is flowing. Let's say the velocity of the river water is once again 1.5 meter per second. Let's say this is 320 meters. And velocity of the boat relative to the water, I'm going to in the previous question it was 2.5 meter per second, but now I'm going to change it to 1.5 meter per second. So I've basically given equal speeds for the river speed as well as the relative velocity of the boat. And once again, the boat starts from A such that its relative velocity, the velocity of boat with respect to the river, is always pointing towards B, same as the previous question. And B is the point which is directly opposite to point A. So the question is asking, find the drift of the boat. So now because the speed of the water and the relative speed of the boat are equal, the boat will actually never be able to reach point B. In the previous question, the relative velocity of the boat was greater than the velocity of the river, which is why the boat was able to catch up with point B. In this case, that cannot happen. The question is asking the drift of the boat. So pause the video and follows the same process that we did in the previous question, and then you can take a look at my solution. Alright, so in this question, let's say that at some instant the boat is here, let's say at point C. So C represents my boat, and the boat has a velocity of 1.5 due to the contribution of the river velocity and the relative velocity of 1.5 pointing towards B. So now you should be able to see why the boat will actually never be able to reach point B, because if you notice, if I write this angle as theta, the x component of the boat will be 1.5 minus 1.5 cos theta, which will always be greater than or equal to 0 because cos theta is less than or equal to 1. So if the x component of the boat, I'm taking this as my x-axis along the river, so if the x component of the velocity of the boat is always towards the right hand side, how will it ever reach point B? It won't. So that is the reason why the boat will never reach point B. And the question is now asking the drift of the boat. So the drift of the boat was basically the component of the displacement of the boat along the river. So let's do that on the next page. So there are two methods to do this. You can do it in the ground frame or the river frame. I'm going to do it in the river frame. And even if you do it in the ground frame, you'll of course get the same answer. But let me just do it in the river frame. So in the river frame, the speed of the boat becomes a constant 1.5 meter per second. And the point B is now moving to the left in the river frame, which was point B was stationary in the ground frame. Now it's moving to the left with a speed of 1.5 meter per second. So my boat starts from point A and its velocity is always directed towards point B. So at some instant, let's say this is the situation. The velocity of the boat is 1.5 meter per second and the velocity of point B is 1.5 meter per second to the left. Let's say this angle is theta. Let me take this as my x-axis, y-axis, x coordinate. Now let's say boat is point C. So CB is equal to L, and I want to write the rate of change of x and L. So dx by dt will simply be 1.5 cos theta, which is the x component of the velocity of the boat, and dl by dt, point B is traveling to the left with 1.5 meter per second, point C is traveling towards B with 1.5 meter per second. So dl by dt is going to be equal to, let's say this angle is theta, so it is going to be 1.5 cos theta is a component of velocity of B along the line joining B and the boat, minus 1.5. So this 1.5, that is the velocity of the boat, is trying to decrease the length L. Alright, so what I'm going to do is I'm going to integrate this equation. But first let me just eliminate cos theta right away, because I can write down 1.5 cos theta is nothing but dx by dt. So can I just write down this equation as dl by dt is equal to dx by dt minus 1.5. So dl is equal to dx minus 1.5 dt. And now I have to integrate this. So this equation is what I want to integrate. So let me just do that on the next page. So let me just write down that equation. dl is equal to dx minus 1.5 dt. So if I look at the limits that I want to apply, so initially the boat was at point A and point B was here. So the distance between point B and A, so this is at let's say t equal to 0. This distance is nothing but 320 meters. And the x coordinate of A is of course 0. So when I apply the limits, initially the boat has 0 x coordinate. The distance between the boat and the point B is 320 meters and the time is 0. And at capital T time, the boat has traveled here and let's say that point B is here. So this distance will become L. Now what is the distance traveled by point B in time t? That will simply be 1.5 times t, velocity into t, and therefore the x coordinate of the boat would be 1.5 t minus L. So we want L, we want the final distance between the boat and point B. So the value of L finally would, I can simply write it as L. The x coordinate would be 1.5 t minus L and the time would be t. So I'll have L minus 320 should be equal to 1.5 t minus L minus 1.5 t, and you will get L as 160 meters. So this L 160 meter is the final distance between the boat and point B. So what that implies is that if I look at it back in the ground frame, remember we were doing all of this in the river frame. In the ground frame, the boat has traveled a distance or a displacement whose component is 160 meters along the river. Point B will be stationary in the ground frame. So basically this will become my drift. Now let's look at graphs in kinematics. So I'm going to be talking about 1D motion. So suppose a particle is traveling along a straight line. If I plot the displacement of the particle versus time, the slope of this graph is simply velocity, ds by dt. If I were to plot velocity versus time, the slope would be the acceleration of the particle. Now in velocity versus time, the area also has a physical interpretation. The area would simply be, because it's going to be integral v dt, it will simply be the displacement. The displacement from let's say t1 to t2. So the total area would be the displacement of the particle from time t1 to t2. Similarly, if I have acceleration versus time, the area under the graph here would be integral a dt. So integral a dt, because a is nothing but dv by dt, I can write this as integral dv. So from let's say velocity v1 to v2. So it will simply be the change in velocity. And another important graph sometimes is given as a versus the displacement. So here the area integral a ds, I can write area as v dv by ds. So therefore this will become v dv, and therefore this will become v2 square minus v1 square by 2. v1 and v2 are the initial and the final velocities. So that will be the area under the graph for acceleration versus displacement. So these are the usual graphs that you will encounter in kinematics. So for example, if you have a simple graph, something of this sort, and let's say this area is A1 and the lower triangle has an area A2. So from let's say 0 to let's say capital T, the distance and displacement, both of these can be asked. So if I look at displacement, I will simply the integral of v dt, which is basically the area under the graph here. So here we have to realize that in the lower triangle of the graph, we will have to put a negative sign with A2. That is because the velocity in this region, in the red region, velocity is negative. So displacement in that region will also be negative. So my total displacement from 0 to t would be A1 minus A2. Whereas the distance is the value of the length traveled. So that will simply be A1 plus A2. So I hope you've understood how we can calculate distance and displacement from a VT graph. Now let's look at a specific situation of constant acceleration. Constant acceleration or uniform acceleration. If I take the case that the initial velocity is positive and the acceleration is also positive, my velocity versus time graph, because v is equal to u plus at, you can see this is a linear graph. It's like y equal to mx plus c. So x coordinate is time, y coordinate is the velocity, and the slope is the acceleration, and the y-intercept is the initial velocity. So my graph will simply look like this. If acceleration is positive, if acceleration is negative, then you will have a negative slope in this manner. What about displacement? If I plot displacement versus time, see, displacement is nothing but ut plus half at square. So this is a quadratic. Now if acceleration is positive, so t squared coefficient is positive. So you can see the roots. Roots are 0 and minus 2u by a. So the roots are 0 and minus 2u by a. That means the graph is a very simple quadratic graph that you can plot. So you'll have one root at t equal to 0 and another root at minus 2u by a. So basically that will be my graph for displacement versus time. If however acceleration is negative, then here the coefficient of t squared would be negative. So my displacement versus time graph, the graph will look something like this. So this is just basic plotting of graph for a quadratic equation. And of course, if you want to plot velocity versus time, that is very straightforward. This is a straight line with a negative slope. So usually such a question can be asked in the case of a free fall, because that is uniform acceleration. So let's just take a look at that on the next slide. Suppose I have a particle that is thrown upwards and then it will come back down. So for this entire journey, I want to plot some graphs. So let me take upward as positive and I want to plot velocity versus time, speed versus time, displacement versus time, distance versus time. Let's also plot velocity versus displacement. So if you want, you can pause the video and try plotting these graphs on your own, and then you can take a look at what I do. Alright, so first thing is I'm going to take upward as, I've taken upward as positive, so my acceleration is downwards. So initial velocity is positive and acceleration is negative. So therefore, if I plot velocity versus time, that graph will look something like this. The total time of flight will be 2u by g. So initial velocity, let's say, is u. So final, it will come back down with a speed also u. So velocity will be minus u. What about speed versus time? Speed versus time is very straightforward. Speed is basically the modulus or the magnitude of the velocity. So all we have to do is make the negative portion of velocity on the positive side. So this will be my speed. Then I have displacement versus time. So displacement for this situation, positive velocity and negative acceleration, we already saw how that looks like. So the displacement is going to be in this form of a parabola. It will reach a maximum height and then come back to zero displacement when it returns to its original position. And that time of flight would be 2u by g. And what about distance? So here, so displacement and distance will be the same till the point, till the particle reaches the highest point. After that, it takes a U-turn. The first half of the journey, displacement and distance will have the same graph. The second portion of the journey, since the distance continuously increases, we are adding the length of the path traveled to the total distance. So instead of the graph going downwards, we just have to continue the graph upwards. So this will be my graph of distance versus time. You should be able to recognize that this portion, the second half of the displacement, is basically, we've just reflected it upwards to calculate or to plot the distance. And finally, let's also plot velocity versus displacement. say if I have the equation for velocity, I can write v squared is equal to u squared minus 2gs. Now if I look at this equation, see s versus v is a parabola. So I want to plot velocity versus displacement, but let me just first plot displacement versus velocity, because that will be just a little easier to plot. So I have displacement as v minus v squared by 2g plus u squared by 2g. So you should be able to see that the graph of displacement versus velocity would be of this manner. It's a parabola. When the displacement is 0, the velocity is positive u as well as negative u, because the displacement will be 0 at the initial position and as well as the final position when the particle is coming down. Now here we can also indicate the direction of time, because I know that the velocity is going from positive u to negative u in the entire journey. So this arrow will denote the sense of time. Now what do I want to actually plot? I want to plot velocity versus displacement. So we'll just simply rotate the graph. You should be able to see that it will be a parabola in this manner, positive u, negative u, and the time would go from positive u to negative u. So that will be my velocity versus displacement graph. So now let's look at a question based on the graph concepts that we've learned. A car accelerates from rest at a constant rate alpha for some time, after which it decelerates at a constant rate of beta to come to rest. If the total time elapsed is t seconds, then calculate the maximum velocity attained by the car and the total displacement traveled by the car in terms of these quantities. So what we are going to do is we can solve this question just using the equations of motion, but it's a little quicker to do it using graphs. So let's take a look at how we can do that. So in such questions where you have acceleration as well as deceleration, it's always best to plot the velocity versus time graph. VT graph is the most useful because it can give us two informations. The slope of VT graph is acceleration and the area is the displacement. So let's just plot the VT graph. So velocity versus time. So the question says that the car starts from rest and accelerates at a constant rate of alpha. Okay, so it accelerates at a constant rate of alpha, and after which it decelerates at a constant rate of beta. So it's uniform acceleration and uniform deceleration, which is why the VT graph is consisting of straight lines, and the total time elapsed is t. So this is this time would be t. So calculate the maximum velocity reached. So let's say that the maximum velocity here would be v naught and the total displacement. So I need the area under the graph. So if I look at the slope of this red line, the slope of the red line is alpha, and therefore can I say that let's say this time is t naught. Can I say v naught by t naught is alpha? And similarly, this time interval would be t minus t naught. So I can also write v naught divided by t minus t naught would be beta, because the deceleration, which is the magnitude of the slope of the blue line, is beta. Now all I have to do is eliminate t naught and get the maximum speed, which is v naught. So that is very straightforward. This is my first equation, this is my second equation. So from the first equation, I have t naught is v naught by alpha, and I also have t minus t naught is v naught by beta. So let me just substitute t naught here. So that will give me t minus v naught by alpha is equal to v naught by beta, and that's it. You can get v naught as alpha beta t divided by alpha plus beta. So this is your maximum speed attained during the motion. And what about the total displacement? That is simply the area of this triangle. So the area of the triangle will simply be half into base into height. So the base is nothing but t and the height is nothing but v naught. So I already know v naught, so it makes everything very simple. That's it, alpha beta t squared divided by twice of alpha plus beta. This is your displacement in the time t. So you can see graph has made such questions very easy without resorting to any quadratic equation that you might have had to use when you use ut plus half at squared in order to calculate the displacement. Let's do another question. Alright, so here I have a velocity displacement graph here describing the motion of a motorcycle. So v versus displacement. And the question is asking us to plot the acceleration versus displacement graph of the motion and determine the time needed for the motorcycle to reach the position 120 meters here. And we've been given the value of ln5. So first thing that we should know that if velocity versus displacement is a straight line graph, ms plus c. M is the slope, c is the y-intercept. Then acceleration, I can write it as v dv by ds. V is ms plus c, and times the derivative of velocity is nothing but m, which is the slope. So this will simply be m square s plus cm. So it's a very nice relation that if velocity is a linear function of displacement, acceleration is also a linear function of displacement. And the acceleration versus displacement will always have a positive slope. Now in this particular situation, the y-intercept, which is 3, is positive, slope is also of course positive, and therefore the acceleration versus displacement graph for the first 60 meters is going to look like a straight line. So let us also quickly figure out what the values of the y-intercept will be. Here I have velocity as the slope is 1 by 5. You should be able to see that from these values of the graph. So 1 by 5s plus the y-intercept is 3. So acceleration versus displacement would be 1 by 9s plus y-intercept is 3 for the velocity versus displacement graph, and the slope is 1 by 5. So this will be 3 by 5. So the initial acceleration would be 3 by 5, and this will go on till 60 meters, after which the velocity becomes a constant, and therefore the acceleration will then be 0. So this will be my acceleration versus displacement graph. Now I want to find the time needed for the motorcycle to reach the position 120 meters. So here we will have to use a little bit of calculus. So if I look at the journey in two parts, the second part of the journey is at constant velocity. So the time taken for the second part would simply be the displacement, which is 60 meters. So 60 divided by the speed, the constant speed is 15. So that will be 4 seconds. So for the second portion of the journey, the time is 4 seconds. Now the first portion of the journey we'll have to use calculus because velocity is a linear function of time. So let's quickly do that. So I can write ds by dt is equal to velocity, which we found out as 1 by 5s plus 3. Let me just write this as s plus 15 by 5. So I'll have 5 ds divided by s plus 15. The integral would be dt. So the limit t equal to 0, displacement is 0. We want to find the time when the displacement becomes 60 meters. So when the displacement is 60, time is t. So I'll have 5 ln of s plus 15. Just apply the limits 0 to 60. So you'll get the time as 5 ln 5. So that will be 8 seconds because ln 5 is 1.6 plus the time from 60 to 120, which we found out as 4 seconds. So the total time would be 12 seconds. So that will be your answer. So I hope you've understood how we solved a question that combined graph as well as calculus. Let's do another type of question that can come, qualitative question. So I'll just plot the graph that you can be asked to analyze. So suppose I have velocity versus time graph. So the question that can be asked here is the particle speeding up or speeding down, and is the magnitude of the acceleration increasing or decreasing? So these are two type of qualitative questions that can be asked. So in this particular graph, it's very straightforward. You can see the velocity is increasing. The magnitude of the velocity is of course increasing. So it's going to be speeding up. Speed is increasing. And what about the acceleration? The acceleration is basically the slope. So acceleration is positive, the slope is positive, and its magnitude is increasing. The graph is becoming steeper, and therefore the magnitude of acceleration is also increasing. So pretty straightforward. Let's look at another couple of problems of this sort. So you can just write out on your own. So I'm just going to give you a couple of graphs, and you should try and figure out whether just basically try and answer these two questions. Alright, so just try and figure out whether the particle is speeding up or speeding down, and whether the acceleration, the magnitude of the acceleration is increasing or decreasing in all of these graphs. And then you can take a look at my solution. Alright, so in the second graph here, I have the speed, of course, decreasing because the magnitude of velocity is decreasing. So speed is decreasing and the graph is becoming steeper. So the magnitude of acceleration is increasing. So you should realize that the acceleration here is negative because there is a negative slope, but the magnitude of acceleration is still increasing. In the third graph, the magnitude of velocity is becoming smaller. Even though the graph is going up, the velocity is negative. So the magnitude of velocity is getting smaller, so it is speeding down. So speed is decreasing. And what about the slope? It's going from a steep graph to a flat graph. So the slope is becoming, the magnitude of the slope is decreasing. So therefore the magnitude of acceleration is decreasing. In the fourth graph, I have the magnitude of the velocity again decreasing. It's going towards the x-axis, so it's going towards zero velocity. So therefore the speed is decreasing. But what about the magnitude of acceleration? It's having, the graph is becoming steeper. The magnitude of acceleration is increasing. And in the last graph, the magnitude of velocity is increasing. So therefore the speed is increasing. And the slope of the graph, so initially it is steep, then the magnitude of the slope decreases, so magnitude of acceleration is decreasing. So I hope you are also able to figure out these answers for all these graphs, and I hope you've understood how we can identify such type of qualitative questions. Now let's look at sort of different type of problems that can come in kinematics. So what I call as intersection problems. So I'm going to start off with an example. So I have two lines at an angle, and the blue line is translating upwards with velocity v1. The red line is translating downwards perpendicular to the line with velocity v2. The blue line also has a velocity perpendicular to the line itself. So the question is asking us, find the velocity of the point of intersection. So here in such questions where they ask you to find the velocity or the acceleration of the point of intersection, you should realize that it's not a material particle that is traveling. The velocity of point of intersection is basically the velocity of the imaginary trajectory traced out by the intersection points. So at each instant, there will be a different point of each line that will be the intersection point. So the way to do this type of question, what I'm going to do here is I'm going to see how the lines travel in a dt time. So initially, suppose I have the blue line here and the red line here. In time dt, the blue line will go up by how much? v1 dt, and the red line will travel a distance v2 dt in this manner. So what has happened to the intersection point? The intersection point, which was this green point here, is now, so this is the displacement of the intersection point, the green arrow. Now if I can figure out the displacement of the intersection point, and if I divide by dt, that will give me the velocity of the intersection point. So that's what I'm going to do. The angle between the lines should also be given to us. So let's say that angle is some theta. If I just label these points A, B, C, D, my displacement is AC. AC will be the resultant of these two vectors, the AB vector as well as the AD vector. So if I can figure out the values of AB and AD, and I know the angle is theta, I can just write AC would be AB square plus AD squared plus 2AB AD cos theta, just vector addition, and this will be my displacement. Let me call it ds. So all I need to do is figure out AB and AD. Now that's very straightforward because this distance is v1 dt. So therefore if I look at this triangle, so I can simply write AB as v1 dt divided by sine theta from this triangle. AB is the hypotenuse in that triangle, and similarly AD will also therefore be v2 dt divided by sine theta. Same logic, and all we have to do is substitute AB and AD here. So therefore my displacement ds, which is AC, would come out to be v1 square plus v2 square plus 2v1 v2 cos theta. Let me take dt as common outside, dt by sine theta is common, and therefore my velocity of the intersection point would be ds by dt, and therefore that is going to be v1 square plus v2 square plus 2v1 v2 cos theta, the whole divided by sin theta. So that will be your velocity of the intersection point. So I hope you've understood how we did this. You have to realize, once again I'm stating, that this intersection point in such problems, the intersection is not a material particle. It's different particles of the two lines that are representing the intersection point at different instants. Let's take a look at another question. So suppose I have a circle. The circle is fixed. This dotted line is the diameter. Let's say the radius is r. And I have a line, blue line, parallel to this dotted diameter that is traveling with velocity v, perpendicular to the blue line. So once again I want to find the velocity of the point of intersection. So the point of intersection would be this red point here. I want to find that velocity. So I suggest that you pause the video and give it a try, and then you can take a look at my solution. Alright, so what I'm going to do is, let me just draw the circle here. If I just label this distance as x from the center, so I can write dx by dt is v. That will be the velocity of the blue line. And in dt time, let's say the blue line is shifted here. So if I were to just look at what's happening to the angle, this angle will be d theta. So the displacement, this red arrow, will be the displacement of the intersection point. Can I write that as r d theta? So basically what do I want? I want the velocity of the point of intersection, so displacement by time dt. So I want basically r d theta by dt. This is what I want. Alright, do I have a relation between x and r? So this is x, this is r. So can I say x is r sine theta? And therefore dx by dt, which is v, would be r cos theta d theta by dt. I just differentiate the equation on both sides. So I'll have v is equal to r d theta by dt is what we want. So r d theta by dt, which is the point of intersection ka velocity, that will be v by cos theta. So that will be the velocity of the point of intersection. So I hope you've understood how we've analyzed the kinematics of intersection points. So that's the end of kinematics. Do the assigned homework. See you at the top. Good night.